All right, if I could have people's attention, this is a terrific pleasure for me. We are bringing people together across many different silos, backgrounds, experiences. It's very much in the spirit of two national treasures who are here with us, Dale Hatfield, who hates when I embarrass him, and Julie Knapp, who's going to give a wonderful keynote address. Both Julie and Dale are spectrum and radio engineer pioneers that bring an extraordinary wealth of experience. And Boulder has long been a hotbed for discussions on spectrum technology, policy, and business. What Silicon Flatirons has merely done is provide a platform for those discussions. And that platform is, of course, indebted to Dale's leadership. And Dale's partner in Silicon Flatiron's Spectrum Initiative is Pierre de Vries, who we frankly lucked into as a senior fellow. None of us are quite sure how we got so lucky, but we feel very fortunate. If you look up the word polymath in the dictionary, you'll see Pierre's picture. His knowledge of spectrum technology, policy, economics would suggest that might have been an area he was trained in. But if you thought that, based on how much he knows, you would be wrong about his training. He has had a fabulous career and decided when leaving Microsoft that he wanted to spend time doing what he really wanted, and has thus taken hold with Dale this Spectrum Initiative. And the ambition of today's conference and the work that's happening, it's really wonderful. And that work happens with many supporters, many people who are here in the room today. You'll see your names listed. It happens in a great tradition of cooperation between the law school, where you are now, and ITP. For those of you who I haven't met, I apologize for not having more time to actually be with you today. I will be moderating a panel later. My name is Phil Weiser. I'm the dean here at the law school. But by taking on the deanship, I remove my time from my own. And so I have to make the sacrifice that all deans make, which is very painful in days like today, which is I don't get to stay for a lot of the conference. I just get to help open up the proceedings. And what I can tell you is you guys are in awesome hands, because the people who've envisioned and bring the conference together really have been Pierre and Dale, and they've got some great plans for today. So without any further ado on my part, Pierre de Vries.
Thank you very much, Dean Weiser. This is a wonderful opportunity for us. Thank you very much, every one of you, for being here. And thank you also to all the folks who are on the live stream. I'd like to just give a quick introduction to what we're trying to do here today. The reason why you are here is that you understand that wireless is really important. There's increasingly intensive use of wireless. And whenever there's something that people use very intensively, they start talking about a resource. So folks talk about spectrum as a resource. The other thing that then becomes interesting is to do what I've learned lawyers do very well, which is to find metaphors. So water is a good metaphor for a resource, and it sort of applies to what happens with radio operations, because there are more and more people who want to take water out of the river. And so things that used to work when there are only a few people taking water out of the river, now you have to be a lot more careful about. But the other issue, and so that's an issue that gets a lot of attention, spectrum sharing, interference, and so on. We want to pay attention this afternoon to another issue, which is the quality of the water that you're pulling out of the river. That's also very important, and that's why we use this analogy of pollution. So when we think about radio noise, what is radio noise? On the first panel, where we have the engineering group, you'll hear that it's quite a contentious subject. Defining anything for an engineer is a wonderful exercise. But just in terms of what happens if you have a radio, there's hissing. If you're watching TV, that you lose the TV. You might, when you make a phone call, you might not be able to make your call. The call might drop. When you have a data connection, the speed might be lower than you might otherwise expect, although how you would know what your expectations are is difficult. You may not be able to get a fix on your GPS. So those are all symptoms of RF noise. Now, as you'll hear in the technical discussion, there are different ways of defining it. I have a working definition which I use to just get into the subject, which is that noise is radio frequency interference that's not from an identifiable intentional radiator. So it's RF. We can't identify one person that it's coming from necessarily, and it's not from somebody who intended to do that. So I see broadly three categories as a layperson. The one is environmental noise, so noise from lightning, from space, from all sorts of natural processes, category one. Category two is man-made noise. So this is noise that might come from switching power supplies that drive LEDs or fluorescents. Those are from many radiators. They're not intended, and Julie will actually talk about this in more detail in a second. And then the third is aggregate noise from many intentional radiators. If you have lots and lots of Wi-Fi devices, for example, they are made to have a radio signal that radiates. When there are enough of them, they actually just look like what we call noise. So the goal for today is twofold. The first is to essentially figure out what is the extent of the problem. Is there a problem? Is it getting better? Is it getting worse? Dale and I have been hearing lots of anecdotes, and it's hard to get real good data, and so you'll hear some data today, but we hope that this event will prompt you to ask for more data, perhaps some of you to go and collect more data. And so once we have a sense of what's going on, the second part of that is, so what? So what should the changes in policies be, if any? Do some policies need to be tightened? Are there some that are obsolete that we don't need anymore? So what are the consequences for regulation? So we have a series of panels that will address all those kinds of things. I'd just like to echo Dean Weiser. I'd like to thank the many, many supporters and sponsors of the program. You can see them in the program. And also to thank the law school for hosting us here. Second, to thank the speakers who have, many of them, come a long way, made time, take a day out, probably 2 more days to get here. To thank them for their time, their travel, and the attention that they put into preparing their remarks. And last but not least, I'd like to thank the staff who've actually done all the work, the folks behind the scene, Anna Noskesi, our program director, Laura Littman, the Silicon Flatirons fellow who's working on this, and a cast of students that are helping with this process. So we're going to kick off now with our keynote. We are very honored to have Julius Knapp here today. Of course, Dean Weiser stole my lines. I try and learn things from people, and so the one thing I've learned from Phil Weiser is embarrass the people you respect, because he does that to Dale, he does that to Mr. Knapp. So Julius is a national treasure. As many of you know, he's been at the FCC for almost 40 years now. He's been the chief of the Office of Engineering Technology since 2006. Before that, he was chief of the Policy and Rules Division. He was chief of the lab. And in fact, he's been recognized not just by the incoming chairman of the FCC, but also by the FCC itself with various medals and awards. So there's nobody better to set the tone for our conversation today than Julius Knapp. Please join me in welcoming Julius.
Okay,
Or
great.
you can just use the clicker.
Thank you. That darn bell better give a good talk. It is a pleasure and an honor to be here. Thank you for the introduction for Phil, Pierre, and Dale. It's always great to be with you. How many of you really are familiar with the rules that apply for things like unlicensed devices, unintentional radiators? Just a quick show of hands. Okay, so thank goodness there's some of you who aren't. And for the rest of you, I'll try to make it as painless as possible. So I'm going to talk a little bit about the relevant FCC rule provisions, some of the things that have been going on relative to noise floor activities, and some topics for discussion and observations. So most people, when they think of noise, think about unlicensed devices. we have a set of rules, Part 15, that specifies what you might think of as the EMC requirements, electromagnetic compatibility, for most electronic equipment. It provides for operation of low-power transmitters as well. And there's two basic conditions. You cannot cause harmful interference, and you have to accept whatever interference you receive. So within those rules is this class called incidental radiators. And this is any device that does not deliberately generate RF energy, but does it as a byproduct of its operation. So some examples. Almost everything with an electric motor. Devices that have electrical contacts. The SCR, the light dimmers that you might not think of as generating noise, but they do. Power lines. The insulators on the power lines may not be connected as well as they should be, and you'll have arcing and there's noise generated. Active antennas. We had a very famous case with, you might say, well, how can an antenna generate noise? Well, we had these active antennas, the little round ones, that were put not only for most consumer use, but in trailer parks where the electronic circuitry that was used to amplify the weak signal from the antenna went into oscillation and was causing interference to paging systems nearby. And they were really hard to track because they were on trailers. And what they noticed is that in the summertime, the interference was up north, and the interference was down in Florida in the winter. So some of our folks were going around knocking on trailer doors, and if you were the owner of one of those mobile homes, you would have been shocked to think that you had anything that was going to cause interference. I have no idea what this thing is on the lower right. This was drawn from some of the older slides we had around, but just to illustrate things you might not think of as noise generators, sewing machines, vacuums, and so forth. So then we have unintentional radiators. These are things that actually may have an oscillator circuit, a clock circuit for timing. Probably best known examples here, computers, peripherals, even the DVD players, the pads and the MP3 players, the tablets, e-readers, virtually anything with electronics in it generates deliberately some sort of timing signal and for the microprocessors that are in them, and they generate some noise. So I'm not going to walk you through. Let's see if we can get this to, no, the pointer's not working. So there are generally two classes of devices. One has got a set of radiated limits that are about 10 dB less stringent for products that are going into commercial applications. So they're 10 dB more lenient and than the general devices that might tend to be used anywhere. And you say, well, why? What's the rationale for that? Well, first of all, these rules were adopted more than 30 years ago. And there's a couple of interesting things. First of all, notice that they were based on a separation distance. So when they're not designed to prevent interference from somebody who takes a receiver and it's a meter away from the source. Well, why? Well, perhaps back then we didn't have as much in the way of mobility as we have now. But there was a rationale that it costs money to suppress the emissions. And there's got to be some sort of balance here between what's practical for the devices. And once you start getting that close, at least back then, it was intra-user interference. You might say that's not so much the case now because we have our own products that are operating closer together. So the limits for the general use were based basically on a 3-meter separation, and the commercial a longer separation, thinking that these are going to be machines and offices, they would be separated. The frequency breaks are kind of interesting too, if you look at it. So you had one level that went up to the low end of the FM broadcast band. Then you had another one that went through the FM and the VHF, upper VHF TV band. And then you had another limit that was more lax above 216 megahertz. And then once you got above 960, another flat level. Well, you can argue a little bit that as you went up in frequency, the propagation losses are greater, so the signals don't travel as far, and there's some rationale for that. But I can also tell you that, so you say, how did you come to these numbers at the time? Well, there was an analysis done by industry, and the dominant concern at the time was TV broadcasting. And it turned out that the analysis for most of the other services, the protection levels were less than what was needed for TV in the direct. So let's talk a little about digital devices. So this is any device or system that uses timing systems in excess of 9,000 pulses per second, and uses digital techniques, including telephone equipment, but exclusive of transmitters. We talked about the two classes, but note that there were big exemptions. So one was for appliances. Another was for transportation vehicles, cars, test equipment, and industrial control systems and others. Well, why? Well, first of all, the industries came back and said, we've been around for years, we haven't bothered anybody, nobody's complained. We have motors that are generating noise, so why are you worried about the signals from our microprocessor? And it was true. I mean, there really hadn't been any specific instances of interference to report on these. They'd been around a long time. It might surprise you that vehicles back then were a concern. There was a lot of consternation about the ignition systems in automobiles. I still remember in my early days at the lab putting cars on a turntable to measure just how much noise there was from these things. And vehicles have got far, far more electronics in them today, but one of the things that helps self-police it is that they can't interfere with themselves, so they really try to reduce the noise. So the US wasn't the only place that had these kind of limits. Internationally, there's an organization called CISPR that adopted standards pretty similar to the United States. So when you think about, if you were to think about changing emissions limits, you'd need to think about, well, this is really a worldwide phenomena. Today, with all of the international travel and people coming from around the world, you would still have all of these products subject to emissions from these kinds of levels from other countries as well. So let's talk about intentional radiators. Intentional radiators, any device that intentionally generates and emits radio frequency energy by radiation or conduction. So the rules for the unlicensed devices specify the frequency bands typically that they can operate in. They limit the power generally to low levels. There are provisions for, in some cases, point-to-point operations at 4 watts CIRP or higher. People often talk about the unlicensed bands. And it's a little bit of a misnomer. There are a handful of bands where these were the bands used, I'm going to talk about this in a minute, industrial, scientific, and medical equipment. There's actually some allocations for other services in these bands, but the most popular, are at 915 megs at 2.4 and in the 5 gigahertz range. But they're not really, that's where unlicensed is permitted to operate. At these higher power levels, started out with rules, where's Mike? Mike Marcus is in the back. Mike was leading a spark for the creation of the spread spectrum rules that focused on these bands and led to a lot of the technologies we're using today. The rules just specify limits on either power or signal strength. They don't specify the standards themselves. So often the industry goes off. That's Wi-Fi and Bluetooth. They're all standards developed by the industry. And sometimes they'll develop out-of-band emission standards for their own self-protection that are tighter than what we might have in the FCC rules. And we've got, for most of these, out-of-band emissions limits as well, and limits on spurious and harmonics. So just some examples. You know, often I'll have people say, gotta do something about those unlicensed devices. And just pull out of your pockets all the things that you have. I mean, there's unlicensed devices, even in the mobile products that we carry around, the Wi-Fi, Bluetooth, near-field communications, the car door openers you have, the RFID, and so forth. So they proliferate basically in every part of our lives, and we carry them. So then there are these restricted bands of operation. Well, why were certain bands restricted? Typically, these were bands where they were either for safety services or services that are using signals that are extremely weak. And so there were specific prohibitions about deliberately operating in these bands, and there's a list of them. It was hard to keep from having every band listed as a restricted band. You know, naturally everybody said, well, don't put them in my spot. But these tend to be things like public safety bands, satellite receive bands, and things like that. So let's talk about ISM equipment. Industrial, scientific, medical. This is equipment that generates and uses RF to perform some work other than telecommunications. So some of the historical examples, and this goes back to like 1927. I wasn't there. But it's used for things like dielectric heaters, food tempering equipment, and then what most consumers have, microwave ovens. So how did this get started, this whole idea of ISM bands? And it does go back to like 1927. They were getting interference, I think at the time it was at 27 megahertz or so, from medical diathermy equipment. Doctors were using high-powered RF to treat people, and they were kind of spread all over the spectrum, not just at 27 where they ended up. And so in the United States and the rest of the world, they came up with this idea that said, well, here's what we'll do. Let's carve up slices of the spectrum where we'll keep all of those, and we'll keep it out of the way of everybody else, and we'll let them have unlimited energy in those bands. So the incentive is unlimited, radiate all you want. Well, it worked somewhat. A lot of these systems, there's an emissions limit that's pretty high outside the ISM bands, and for various performance reasons, they operate outside the bands as well. So two new phenomena that we have seen come in the last few years is wireless power transfer. A lot of work going on charging your electric vehicle by radio, and growth of RF lighting. I'm going to skip through this in the interest of time. Now, the licensed radio services. So licensed transmitters emit energy too, both in band and out of band. There's a kind of rule of thumb out of band limit that we've had, I think, since the dawn of time, and Pierre's done a lot of work on this. That the emission has to be suppressed by 43 plus 10 log the power. It works out that it's minus 13 dBm, no matter what the power is, because it's proportional. but we've applied more stringent limits in many cases, depending on what's adjacent or where the harmonics fall. And often the industry, particularly I think through 3GPP, the wireless industry standards are much more strict than this. One of the things that drives this is that today's licensed transmitters have got multiple products in the same device. So they have an incentive to reduce noise so they don't interfere with themselves. But applying these limits has become a lot more complicated. Early in my career, what you did is you turned on a transmitter. It did one thing. It had one modulation format, it was one bandwidth, and you turned it on and you made the measurements and you were done. If you were to pull up, and all this stuff is available, you go into the FCC Equipment Authorization Database and start looking at the test reports for some of this equipment. Not only are they multi-band, but in every band they can have multiple bandwidths. They can have multiple modulation formats, and you start to map it out, and you're doing, how many tests do you do for each one of these things to determine compliance with an out-of-band or spurious emissions limit? So it's just not as simple. And when I mentioned that the devices include multiple transmitters, so aside from that is which ones can be on at the same time? And so you might think, well, I'll just test one, and then I'll test another, but what if they create intermod products? So I'm just going to say a little bit about, and I know I'm not doing it justice here, some of the activities on noise floor. There have been some organizations that have focused on noise floor for years. Obviously, the ITU has issued reports that provide information on how you can estimate generally the noise floor for particular environments and particular operating conditions. So ITU publishes reports and recommendations on that. There's a group, I don't know how many of you may have heard of it, called the International Union of Radio Science, or IRSI. They meet about every 3 years, and they have been studying noise as well for as long as I can remember. The National Academy's Committee on Radio Frequencies, or CORF, they're focused primarily on radio astronomy, but they also keep tabs on radio noise, which, by the way, radio noise is often a real key issue for radio astronomy across the board. And then there's others like the ARRL and voluntary standards bodies that do work on suppressing noise. At the FCC, Spectrum Policy Task Force was created, and in 2002 recommended the Commission undertake a systematic study of the noise floor. And actually our Technological Advisory Council started a project to look at the noise floor, and it was funded. The first step in that was to create basically a bibliography, a list of all of the publications, and that's as far as it got. And it's not that folks really didn't care about this. It's just, I think it's symptomatic of the difficulty of trying to get your arms around noise and not only how to measure it, what's the impact. I'll say more about that in a minute. And the Commission has asked about harmful interference and what constitutes harmful interference in many proceedings over the years. I think that's the holy grail of interference control, is a more specific definition of harmful interference. So some food for thought as we go through the day. There's no question the radio spectrum is a critical resource and it should be protected. The current state of radio noise is difficult to get your arms around. There's a lot of anecdotal reports you'll hear in the hall. Oh, did you see at the show when everybody turned on how the noise floor went up? Or we went out and we were doing some measurements and we were really surprised to see a higher noise floor. But there's not, at least that I'm aware of yet, a wealth of information about measurements and scientifically derived tests measuring it. And I think as you went through Bob Matheson's presentation, you can kind of understand it's just not as simple as you think. You may stick an antenna on a spectrum analyzer and think you know what you're looking at, but all those questions about what kind of detector you're using, do you look at peak, do you look at average, do you look at quasi-peak, what bandwidth is it, they all make a difference in what you're going to see. I would suggest that it's important to keep it in perspective as well. Radio noise has been rising since the first radio was turned on. This is not really a new phenomena. So it certainly merits discussion, but I think trying to get our arms around what the levels are today and what's the impact of that. The technologies that have been introduced more recently tend to be more robust. But there are also some pluses and minuses to that. They'll be robust up to a point, and then they just go over the edge. So they may be more tolerant of the noise up to a point, and then it's all or nothing. The flip side, too, for the digital communications, when we talked about noise in the past, typically the out-of-band emissions were spikes or narrow-band harmonics. Now the emissions actually tend to fall off with some slope continuously. So it's a little different set of technical characteristics than we had before. So ideally, I think we'd all agree we'd like to see the radio noise be 0, as long as it's applied to somebody else's products. It's really not practical to do that. Noise, I think, is something to be managed. And the real challenge is what's the right balance between noise and noise control, and things like the cost and the impact on devices and the viability of meeting those standards. So I could set standards for a laptop here that says I want to reduce the noise down to below the background noise level, and then I'd probably be walking around with a laptop I can't carry. So there has to be some balance. So the costs and benefits, it's really critical to be thinking about this. I see Rob Aldifer out here. Rob would never let anything go out of the commission while he was there without a cost-benefit analysis. It was kind of our rule of thumb, and Rob was terrific at it. But it's difficult to quantify the cost because there are numerous sources of noise. There's little data on which are the most significant contributors. The scope is a major factor. Are we talking about controlling noise in just one part of the spectrum, or is it all parts of the spectrum? Where is it potentially problematic? And then the cost and the viability of meeting it really depend on what the standards are that are set. And it's difficult to quantify the benefits. So at what point is radio noise harmful interference? This term that we use to say whether something needs to be done. Noise is a combination of natural noise sources, and I don't know that man-made is politically correct anymore. Person-made, but and I think Pierre hit the nail on the head. You may not always be able to identify a specific source. So what are reasonable targets for noise levels? If you were to do that, how would it potentially reduce the infrastructure costs? Would you build fewer towers, for example? What would the impact be on improved service quality and reliability? I think it's easy to talk about things like dropped calls and so forth, but making a direct connection between that effect and what the causes are is not always so clear. And then can technological solutions mitigate the impact? And so, yeah, there's noise there, but are there solutions that can be built into the systems and the technologies that address it? So some closing thoughts. I think we need to be careful not to leap to conclusions. You know, I'll often hear people say, well, there's lots of noise, go and put a stronger emissions limit on product X, without really having made the connection between the two. The other thing to think about is your desired signal may be noise to somebody else. So, how many of you are on Wi-Fi? How many of you are generating noise? All of your hands should stay up. So, you know, it's important to keep in mind that these signals that are on the air are often serving a useful purpose. And even within your own service area, you know, your signal doesn't stop at the edge. And yes, you work it out with your neighbors and so forth, but the minute you go on the airwaves, your desired signal can easily be somebody else's noise. We're going to talk about the environmental models, and I'm eager to hear about that, but just I would suggest to think about how well they translate to the radio world. So for environmental, you may have an incentive that says you're going to have some lower costs or assessment if you have reduce a certain type of emissions. When we talk about radio, it's not so clear because the emissions can be all over the place. They vary with the mode of operation and so forth. And each individual device may have very little impact. And I'm not sure what the incentives would be. So I also agree with Pierre, you know, that the questions of, well, is there a problem? And if so, what steps, if any, might be appropriate? And so I look forward to the discussions today. Ran a little bit over. Thank you for your attention. Sure.
It's a privilege to have Mr. Knapp here, so let's take a couple of moments. If there are a couple of questions, we'll entertain them, and we'll use the Silicon Flatirons rule of students get precedence. So if there are any students that have a question, let's just first see if there's a student available. Nope. Sir, please. Mr. Gunn.
Let's assume that someone came up with ways that might mitigate or improve.
Could you just hang on a second? We've got the microphone.
Oh, I'm sorry. Okay.
Thank you. William Ganter, Custom Link Corporation. Assuming one came up with methods that might address some of the improvements, how does one get that into an FCC look or review to say, ooh, this might be better, or no, it isn't, type of thing? So,
And not everything is about rules in the commission. So I mean, in the TAC right now, the Spectrum Working Group has been looking at things like interference cancellation technologies. Are there things that are emerging that can deal both with the kinds of traditional harmful interference and reducing noise? So we're always open to learning about, you know, the latest developments and how you take that into account. But also on the flip side, I haven't seen any magic bullets yet.
Scott Townley with Verizon. You mentioned, and the previous commentators have also mentioned to this point, the lack of data on man-made radio noise. And perhaps that would be formal scientific campaign lack of data. But I know my company and any other carriers that are in the room with me, wireless carriers, probably have reams of data of anecdotal measurements that we've made against various sources and stuff. We all have it and know what it is, but we're the only ones who have it and know where it is. It kind of leads me to wonder out loud, does there need to be some repository of this for review by the industry as a whole? Right now, the only repository I'm aware of is the Enforcement Bureau. And even at that, I don't know that we provide much data other than we're experiencing harmful interference, come help us out.
Yeah. And I think that's a good point to discuss as we go through the day and beyond. I think of it as this is a community issue, as opposed to I operate in this band and somebody else is generating noise into mine, because even though, and I think the wireless industry pays a lot of attention to controlling the noise out of its systems, but it's also, it generates noise in other bands, and so there's other players out there who may argue, well, the noise in my band should be less. And I'm not sure what the right forum is for that. But just the awareness that it's not just my band, but this is really a community issue.
Right, so to follow real quick on that, and this is I've had this response a couple of times today. This is not necessarily only a carrier-to-carrier issue. This is really primarily a carrier-to-unintentional radiator issue.
Mm-hmm.
So, and along the lines of awareness of scope of the problem, what types of problems there are, and this is really why I'm here, whether there's any regulatory relief or movement in that direction. A lot of the stuff that we know exists, we're the only ones who seem to know it exists. Mm-hmm. So hope maybe today will help that problem.
Good.
We'll close on that one. That's a very good point. In fact, there was a group of us who were discussing that very issue this morning. And I think it's something that Dale Hatfield has expressed interest in as well, finding a group of people to be a repository, a neutral third party that can aggregate that. So if there are any carriers that want to pursue that, please get in touch. We couldn't have had a better keynote, a better set of questions. Please join me in thanking Julie Knapp. That was a very good keynote. So we'll move right into panel one. If the panelists could just join me up here at the podium. Good. So this is panel one. This is a discussion about measurement. So this is the engineer's ghetto. We have a very illustrious group of folks. The main speakers will be Jeff Wepman, Frank Sanders, and Mark McHenry. There is information about their bios in the leaflet if you'd like to look that up. We're also honored to have Bob Matheson and Dale Hatfield join us for this panel to provide their thoughts. What we were trying to do with this panel is just to start this conversation about what is this stuff and what's known about it. We'll have a conversation on the panel for a little while, and then we'll open it to the audience to discuss it a little bit further. So let's just start, Jeff. We've talked about noise. We talk about interference. So how do we think about the difference between those two things?
Well, first of all, I think trying to distinguish between noise and interference is a pretty difficult topic, and it's really subject to, I think, a lot of different interpretations. I've gone out and actually done a lot of noise measurements, and I like to use a specific interpretation specifically for the kind of measurements that I do, which are man-made noise measurements. And there I like to look at interference as a phenomenon that arises from intentionally radiated signals, and noise arising from either natural sources like lightning or unintentionally radiated signals that would be generated by man-made sources, like we've heard about in Julius's talk with power lines and automobiles and electronic devices like computers and other devices. For for my noise measurements, what we do is we first ensure that there are no intentionally generated, clearly identifiable signals in the measurement bandwidth that we're going to make. And this really is a pretty universally accepted practice for those making measurements, making noise measurements. And we do this first by doing a formal spectrum measurement, assessing the spectrum, analyzing the data, making sure that we really don't have signals in that measurement bandwidth. Sometimes that's much easier said than done. But
what makes it difficult?
Well, I think you start to get into issues like if you have a transmitter in another band and you've got spurious responses from that transmitter that end up in the band that you're trying to measure, what do you call that? Do you call that noise? Do you call that interference? Do you make the measurement? Do you make your noise measurement with that kind of phenomenon going on in your band? And sometimes it's very difficult to tell the difference. And then you consider these kinds of signals, whether they're below your base noise floor or a little bit above it. It can be very challenging. It almost gets to the point where, I mean, if you were going to do maybe a thorough job with it, you might actually try to demodulate something in your band to see if it actually really is a signal that's being transmitted, or something you want to call more noise.
So what I'm hearing you say is that there isn't a standard definition for the term noise that you would use. You would use it ad hoc in the kind of, depending on the kind of project that you're doing?
Well, I think it's important to realize if you're going to make a noise measurement, and typically what we've concentrated on in the last several years is man-made noise measurements. When you're going to do that, the important thing is to make sure that you don't have a clearly identifiable interfering signal in that band. And so I think we can kind of bound the problem a little bit, because I think if you try to look at the entire picture of trying to distinguish between noise and interference, you may not be able to come up with a good solid definition. I've been in rooms with discussions that have gone on for hours about, this is noise, no, this is interference. But maybe it's not that important. Maybe, certainly when we make a measurement, we can simplify things. Right. And that's what I do.
Great. So Frank, picking up on that in terms of doing the measurements, are there standard metrics in the toolbox that you use for making quantification of whatever this is?
Not necessarily. We do not necessarily have a standard methodology for measuring noise which is recognized and agreed upon between government agencies, or between government agencies in the private sector, or even amongst agencies and organizations worldwide. That is not to say that individual researchers who measure noise do not have well-defined methodologies. They typically and normally do. However, the methodology that's used to measure noise is generally dependent upon what it is that a researcher is looking for. I can measure radio energy, including noise, with certain selections of measurement bandwidth, such as Bob discussed earlier, and certain detection techniques, peak detection, average detection, and so forth, in such a way as to either minimize or accentuate the amount of supposed noise power, noise energy that I'm seeing in a receiver. I can also play games if I want to with the time of day that I'm doing the sampling and that kind of thing. But even putting that aside, what we see when we look for noise is very much dependent upon what the parameters are that we use to search for it. And to go back to some of the earlier discussion, because this begs the question, well, then which ones do you pick? The answer is it depends on what we're looking for. If we're looking for effects of noise interference on a particular type of communication receiver, we might well want to look for the noise with a receiver that has a bandwidth and a detector and maybe signal processing equipment, which is either identical to or very similar to the receiver's characteristics. In some cases, we might even simply modify a receiver that is suspected of being a victim of some sort of radio noise, or that we think might potentially be a victim of radio noise in the future if this type of receiver is going to be deployed in some new spectrum where it's not currently used. However, it's also true that people sometimes want to and need to do more academically oriented studies. If they're doing more academically oriented studies because they want to understand the overall noise environment of the world better, which could include natural sources like the sun, the ionosphere, Jupiter, the galactic center, then they are going to select certain sets of antennas, certain bandwidths and detectors that are good for that. If they're interested in looking at man-made noise, they're interested in looking at noise out of, we'll say, electrical generators, noise from power lines, electrical noise from the unwanted emissions of licensed devices, or noise that might look like some aggregate emission from unlicensed devices. Then what they will probably do, and what I would recommend that they do, is to in fact measure the noise with a variety of bandwidths, several bandwidths that is, and with a variety of detectors, and then condense their measured results down into an understandable, comprehensible set of data. And that's the hard part. People think the measurement is the hard part. The measurement is not the hard part. Reporting the measurement in such a way that people can understand it is the hard part. And the thing that I would recommend that people do is present the data from the various bandwidths and the various detectors in such a way that people can see what happens if they look at the spectrum through a narrow window, a wide window, an average detecting system, a peak detecting system, and then they can take that output, they can take the information that I would give them or someone like me would give them, and apply it to their problems, to their needs, for their spectrum sharing needs, their research, their receiver interference problems, whatever the case might be.
So let me see if I'm following. There's two things which I hear you say at least. So the one is, by implication, folks are not actually careful enough in reporting their data in a way that is reusable by other people because they don't give multiple bandwidth and present the full set of data. But perhaps more problematic, you can't generalize from one measurement for one kind of receiver to another setting. So every measurement really applies only to what the purpose was.
Yeah, I would modify your first comment just slightly and say that people who present radio noise information usually have specific purposes in mind when they take the data, and their data aren't necessarily always very usable by other people. Now they might be, they might be, but just not necessarily. And yes, I would definitely agree also then very much with your second point.
Right. So Mark, turning to you, I mean, we've been obsessing about definitions and measurements. So what are the implications of that?
Well, we spent a lot of time talking about it. It is hard to take someone else's data and use some other place, which kind of delays the acceptance of there being a problem or not. I got into this because I'm involved in spectrum sharing, and in spectrum sharing, they almost ignore the noise because it's so complicated, and hold everyone to a thermal noise background when they develop spectrum sharing rules. So I think that's been a big impediment, the complexity of the problem. Since he can't put a number to his problem, it's kind of just set aside and ignored because it's just too much to absorb.
So is the question answerable, do you think?
You can answer it crudely very quickly, but if you want to get down to dBs, you quickly get into the details. If you want a 5 dB answer, you can skip a lot of the details, except that you'll have some error bounds, what you're doing.
Right. Perhaps you can talk a little bit about the measurements that you've done.
Well, I brought some charts. I gave one or two examples.
Okay, good. So
what we've done is we got involved in building dynamic spectrum access, which is radios that look at the spectrum and try to sense if there's someone there or not. And we went out to Fort Irwin, out to the military, and this was 225 to 450, and the radios just locked up because every channel was full. So we got very involved. So in the last, just about a month ago, I just did some example measurements to bring to this meeting, and we had a portable spectrum measurement system, and we started down in the parking lot of our building in Vienna, Virginia, where it says start right there, put it on a cart, and I just went in the building, up the elevator, and we're on the 7th floor, and wheel it into my lab. So the question is, what is the inside noise in the ground level versus the outside noise? So you can kind of see the
Other way around.
snail trail. Blind someone. There's the snail trail. The GPS kind of had trouble going indoors, and then it jumped around. And there's a picture of the cart, and we actually had the equipment in, and we double shielded it. The equipment is shielded, and we put it in an enclosure. And we have 2 different antennas, and we swept 11 different frequencies. So the next chart just gives some measurements. So this is time this way. This is starting in the parking lot. This is going up, and this is where we close the door. Here's where we open the door. And all these lines are these different detectors Frank was talking about. And there's APD. We took the time domain, the amplitude probability distribution, and the lower one is 10% of the time the signals are there or higher, and the other one is 0.001%. It's basically the max value within the 50 millisecond window. So all these squiggly lines are how amplitude vary. Here we shut the door of the enclosure, started walking, and you can see the line just marched straight up, 10 or 20 dB. And then these are different frequencies. 112, and we did a lot of frequencies, and sometimes you do find or radiated intended signal, and we usually just throw the data out. And you can see as we walk by something, there'd be huge spikes that would line up on several frequencies, and then this kind of aggregate effect going up. And the next chart is higher, even into the pristine life or death GPS frequency. Go to the next chart. And the L1 band is slightly went up. But if I went to the FCC and said I wanted to install a device that made the GPS frequency band go up by 1 dB, the noise figure, there would be a rain of money to go against us. But no one seems to care. Now that's inside, but we've done similar measurements outside.
So you're saying that there's an increase as you go inside?
Yeah, it's slowly going up. I mean, there's some wiggles here, but it's probably a dB. It's probably very small.
Okay.
If it was a half a dB, and I went to the FCC and said I wanted to radiate, they would be told no.
Mm-hmm.
So I guess that's the summary. We're getting involved in this, trying to do spectrum sensing, A, to set a reasonable limit and expectation with the FCC about sharing, and B, so our detectors don't lock up false alarm.
Mm-hmm. You said it's pretty easy to get the 5 dB kind of data. In his keynote, Mr. Knapp was talking about the fact that it's hard to get, there's lots of anecdote, there's not the scientifically validated stuff. Do you know of anybody who's actually done the publications of the 5 dB caliber?
The Boulder guys have probably done the best. They've done, and we actually copy them, and we plot our data like they plot. They've paved the trail on how to make these measurements and plot the results.
Go ahead.
I should mention maybe just one interesting side anecdote, and you triggered this thought, Mark, when you were showing your data and commented that as you moved around, things went up and down, and that, well, it is that noise is not always useless. There are some good uses for noise. Mm-hmm. Not only do we calibrate measurement systems with noise sources under some circumstances, but when I'm doing outdoor measurements and actually indoor measurements for various purposes on intentional radiation and so forth in the microwave part of the spectrum, I routinely search for the noise from microwave ovens that's in the neighborhood, because I know that that noise is pretty much ubiquitous in any civilized area. And if I can see that noise, then I know that my receiver is working.
Right. Bob, did you want to make a comment?
Yeah. First of all, I agree with all these, what these guys are saying. It's very difficult to decide what is noise and exactly how you want to measure it and stuff. One thing that would be worth pointing out is that there is one universal measurement of noise, and that is to make an RMS measurement, a measurement of average power. Whether you're having noise impulses or system noise or whatever, whether you're measuring wide bandwidths or small bandwidths, all reproducible to the same number, RMS dB above KT or some number like that. And
could you just draw RMS above KT? What does that mean?
well, let me see. Yeah, RMS. Someone explain
Well,
dB
so,
above KT.
Yeah, so
Here's a volunteer.
Typically, dB above KTB is 0 dB at room temperature here. If you have an antenna at that temperature and you hook a radio receiver up to it, if there are no signals around, nothing but room temperature, you will get 0 dB above KT. That will, if you double the bandwidth, you'll get twice as big a number, but actually we should be seeing KTB, so it will be the same amount of energy per hertz. And as long as you measure it with RMS detectors, that number will stay the same. Now, on these other things, if you measure it with a very low percentage, or you use a peak detector, then you may get a very large value, or somebody else using a different detector will get a very small value. But the point is that RMS is a good inviolate detector that will serve many purposes well, and it's probably not even too bad a number in terms of saying that the interference is proportional to RMS. Because if you have a strong spike, sure, you'll wipe out a bit, but your error correction stuff will replace that bit. If you have a very low continuous level of noise, maybe it doesn't interfere with everything, or maybe it gets above the threshold and wipes you out. But I mean, so RMS is not a bad value. It's a good starting point.
Yeah, I'd like to add that actually internationally we use basically the RMS power as an accepted metric for measuring man-made radio noise, and even atmospheric radio noise for that matter too. Anyway, I just wanted to make that point too.
And one other point that I should mention momentarily, because this has come up in regulatory situations, is, and going to what Bob said about KT, K is a number called Boltzmann's constant. T is the temperature of whatever you're dealing with. In this room, we're at about 290 degrees Kelvin. By virtue of the action of electrons in matter, this table, our bodies, the air, the walls in this room are all right now emitting radio energy. The amount of radio energy that we're all emitting simply by existing is minus 174 decibels relative to a milliwatt in a 1 hertz bandwidth. When we talk about limiting noise, we're talking about limiting noise that is in excess by some amount of what the tabletop and our bodies and this water bottle are emitting. There have been cases where people have been trying to set really low levels on radio noise and have inadvertently set levels that were actually either at or below that limit of KT for something like ourselves in a water bottle. Now, that's egregious, and normally that eventually gets caught. But it is something to watch out for. It's not like we can get a zero limit. We can only get, as Bob said, zero relative to what we're all producing by merely existing.
So just since we're talking about the big picture here, if we look across a wide range of frequencies, we start from HF, 20 megahertz, go up to 200 megahertz, TV bands, then up into the cellular bands. And we look at the excess over this,
Over the water bottle.
wave water bottle.
What this is radiating.
Does it get better or worse as frequency goes up? Go ahead.
I think the first order may be very similar, except the spatial extent. So the probability of finding them maybe is about the same, but when you do find a radiator, the distance, the lower frequencies are impacted at a bigger distance. But if there's something radiating, it's going to put out reasonable power, maybe up to a gigahertz.
Right.
But the spatial fall, so I guess the impact is much worse at lower, but it's just the 1% of the time you're close enough to see it, or 5% of the time.
Right.
Yeah, I think it's also radio noise phenomenon are dependent on frequency bands that you're looking at. For instance, if you're below your 20 megahertz, then atmospheric noise, noise from lightning is very important and can actually be extremely high, as Bob Matheson was mentioning in his tutorial. As you get above the HF frequencies, man-made noise starts to become more dominant, and that is a phenomenon that has been studied a lot and appears to decrease with frequency. So I think it's important that you consider what frequency bands you're specifically looking at.
So let me sort of play devil's advocate here. So you're saying it gets less of an issue as you go up in frequency. Apart from a few key advocates like Commissioner Pai, who's concerned about AM radio, most people are concerned about, let's say, cellular frequencies above a gigahertz. Do you, from the data that you've seen, either momentary data taken at a particular time or trends, do we actually have a problem above a gigahertz? Do we have a problem in the TV bands?
I think the problem comes into what, it almost comes back to that kind of distinguishing between noise and interference, because now when you're up, we've done a lot of work typically between, man-made noise studies have typically been done a lot between 100 megahertz and a gigahertz. And so definitely the man-made noise decreases in that range from 100 megahertz to a gigahertz, to the point where it's actually difficult to measure once you start getting up probably even above 600 megahertz or so. But I think what is important is that you get this other phenomenon as you get higher up in frequencies beyond a gigahertz. Now you have to start looking at things like what we might call more interference, spectral crowding, aggregate emissions from multiple devices. So that I haven't studied much, and I'm actually not aware of people studying that in detail, like it's been studied with atmospheric noise and man-made noise at the lower frequencies.
I mean, one of the things that we could talk about a little bit is a rough taxonomy of how one categorizes these things. So, for example, questions for you about, does the noise environment differ in different contexts? So, Mark, you showed indoor, outdoor.
I think indoor and outdoor are very different. We go outdoor and make a lot of drive measurements, and it goes right down to thermal noise, and you drive along, and it pops up when you near something, and right down to thermal noise. But indoors, the whole thing comes up thermal noise. Everywhere you move inside, it's up 10 or 20 dB. I think totally different inside and out.
Do you have a theory about what's causing that increase?
I think it's just a cumulative effect. It's
of
the density
of
propagation losses. It's just simple.
Intentional radiators.
Unintended radiators. It's just outside. They're spaced hundreds of meters apart. They're far enough. They don't aggregate. You know, there's thousands maybe within view, but the loss is so high they don't aggregate up. But indoors, there's hundreds within 100 meters, and it aggregates up. So I think the inside and outside are very different.
Well,
And in addition, probably, you've got all these things called wires that connect and act like antennas and so.
No, re-radiating on over.
Yeah, re-radiating, and so it's I would think that the noise would be pretty high inside.
But outside, you know, if 1% of the places it's high, is that worth? You say it's harmful. You have to ask the carriers. If 1% of your locations it's 20 dB above your thermal, do you care?
right. Good. One last comment, and then we'll just see if there's any questions in the audience, and if not, we'll return to the conversation. Frank?
I think that at our Commerce Lab here in Boulder, we're also, at this point, arguably more interested in indoor noise work than outdoor for the same reasons that you've already stated, Mark, that at frequencies above a gigahertz anyway, the outdoor environment tends, I emphasize the word tends, it does vary from place to place and so forth, but tends to be relatively quiet. Indoor environments seem to have more noise activity, seem to be more interesting, and we think should be studied more.
They say now
I would argue
70% of people use indoor cell phone versus outdoor, and that's
Right.
where the use is.
Yeah, because I can imagine that in the past when it was TV and actually cellular was the thing in the boot of in the trunk of your car, it was an outdoor problem. Now all our devices are used indoors. All the interferers are indoors. How much work has there been? Frank, you mentioned ITS has been looking at this. Has there been funding for anything like this?
Not really, no.
Yeah, yeah.
We got a project from the Army to predict man-made noise. They're very worried about it in the range. They call it encroachment, because they are worried the towns will come up next to their test ranges and affect their tests. I think the DoD is very interested in
that's
this.
interesting.
Are they indoor? Are
Outdoor. They
interested
want
in-
outdoor
they're
models to
interested
predict
in
how it
outdoor?
impacts test ranges.
Yeah, good. So let's turn to the audience and see if there's any questions. Again, we'll use the Flatirons rule. See if there are any students that have a question. They always get priority with us. Feel free. Yes, we have a question in the back. Please identify yourself.
John Cook. I'm a second-year law student here at the law school. So we've seen over the past few decades the prime spectrum, the most desired, and right now the mobile spectrum, the frequency range keeps going up. So do you see as the issues with noise decrease in increasing frequencies? Do you think this is a problem that might resolve itself as we keep finding ways and preferring to use higher frequencies for the most spectrum-intensive applications? Did that make sense?
Yeah, so the question is, are you likely to, is the problem going to go away as more of our systems go up in frequency where there is less noise?
Probably.
So would this conference not be necessary 10 years from now?
No, because no one wants to use high frequencies. I mean, you want to penetrate. You want to have long link range. Or rural people. I think it's not going to you can't wish away physics.
Bob?
But indoors that we were just talking about, high frequencies are great, and maybe there is a high noise levels there, but you're only 10 feet from your Wi-Fi radiator, and so it may not be a problem, and it may be that
Costs too much to fix.
well, we don't need to fix it.
What's cheaper for that? Just point in and fix it.
Yeah, we had 2 Wi-Fi boxes in our house so that both the bedroom end and the TV room end can get the signal even in spite of our higher noise. I mean, I don't know whether that's really true, of course, but my impression is that noise may not be a problem if we can just keep adding more transmitters closer and closer together. And I'm sure that people who talk about these smart houses and smart appliances and there's going to be tons more stuff pouring noise into things.
So do we reach diminishing returns? So you're saying solve the problem by adding more and more transmitters. Adding more and more transmitters adds more noise.
I have no idea.
But we're just guessing, and it's a huge impact in society. We should be guessing these things.
Yeah.
So that's a very good point, Mark. You're saying we shouldn't be guessing this. What kind of work is needed? What would you recommend the research community work on to answer those questions?
A lot more of these measurements. Figure out what's the emitters, and is it because of faulty devices or devices that are in spec? All that stuff about regulatory stuff. It could all be things that are oscillating or out of spec, and you could regulate forever. Maybe you should sue the manufacturer when the thing oscillates. I mean, they could be of the wrong regulation.
Was there another comment if you wanted to respond? Okay, good. So we had another question in the front here, please. If we could have the microphone and identify yourself.
Is commentary welcome as opposed to a question? Okay.
Yes, please.
I want to make sure I follow the rules here. But it could be 20 minutes, so stop.
No, the time limit is shorter on the commentary than the
Yes,
question.
very good. Very good. So the gentleman in the back asked if the problem goes away with higher frequencies, which I think there's a general pervasive feeling that the problem does get more diminished at higher frequencies. However, I think Mark alluded to this in his response, which is that's not where we're going. So what, in 2 years we're going to have a 600 megahertz auction for wireless access?
Precisely.
That's down, that's not up, right? Coverage in wireless systems works much better at lower frequencies. You talk about rural coverage, you talk about universal broadband availability for the United States. That's the opposite direction. So that makes the problem worse, and we will be here in 10 years talking about it. Again, Mark's observations that the noise problems are higher indoors and out have been our observations in the carrier community as well. However, that doesn't mean that the impact of those problems are limited only to devices that are indoors. We've had numerous instances where the aggregation of noise from a certain source inside a building overwhelms the exterior cellular network such that no one, indoors or out, receives service from that cell site. So it's impactful over a large area, not just where the noise sources are. And the solution of adding more base stations, essentially, or more transmitters, will work fine in one direction, from the base station to the user, but it doesn't work in the opposite direction, where you have the users that are trying to transmit back to the base station. If that base station is impaired, moving the base station closer to the users moves them closer to the noise. You've not won anything. So there's a two-directionality, at least from the wireless service provider's perspective, on how these problems need to be addressed, and it makes it, as if it weren't complicated enough, it makes it even more complicated.
So let me just ask a follow-up question, since you volunteered this very interesting information. Do carriers know what those aggregating sources of noise are?
We know what a lot of them are. We don't know what all of them are.
Can you give us some examples?
I have a piece of paper. So really, of the aggregated sources, the two largest offenders that we have that we observed in our networks today are high-efficiency fluorescent light ballasts and switch mode power supplies. The lighting ballasts, I think, are kind of obvious in office buildings. That's really the case that we see quite often, where a sector of a cell site is looking at an office building. They've just went to change ballasts to save 10% on our light bill, which is great, except for now that we can't hear anything but the light ballasts. The switch mode power supply one typically tends to be more of a problem in stadiums. This all ends up being a tree falling in the forest problem, right? If it's nobody's there to observe the problem, it's not a problem, right? In sporting stadiums, it's not a problem until game day. They turn the scoreboard on, which has literally thousands of switch mode supplies to run the LEDs, and nobody can make a call.
Yeah.
And then the game's over, they turn the scoreboard off, and everything's fine.
Yeah, very good. Good examples. That's a very good comment. So does anybody want to respond to that? Because I think it actually raises a lot of very interesting questions. One of them is this intersection between noise, measurement of noise, and enforcement issues.
Yeah.
Dale, this is something you've thought about a lot. Can I presume on you to start us off?
Well, I have been thinking an awful lot about enforcement and how those sort of things, turning the stadium lights on and off, seems to me you could kind of figure that out pretty easily, but there may be other situations where you may need to do a lot of de-effing and things like that to be able to actually find that place where it's emanating from. Is that, and then you've got, I think, in enforcement, you've got the enforcement trail too. If you're really going to talk about enforcement, not sort of voluntary actions by somebody, but actual enforcement, then you get into evidence issues and things like that. I mean, what sort of information you need to collect to be able to, that you can then take into court, right?
But maybe they're following the law. You're not even sure there's a violation of the law.
Well, that's a fair comment too, indeed. This goes back to Julie's talk, right?
Mm-hmm. Yeah, in fact, it is often the case that devices that are experiencing interference, victim receivers, are getting interference from other devices that are generating unwanted emissions or noise or some combination thereof that are completely in accord in their operation with all applicable rules and regulations. And in fact, rules and regulations on acceptable emission limits from devices for noise, unwanted emissions, etc., cannot guarantee that interference problems will not occur. And I think that what this begs is the question of, to what extent should devices' emissions be examined for potential electromagnetic compatibility problems, as opposed to simply examining device emissions to see whether they do or don't pass emission mask limits.
And this gets into the ex ante, ex post issue too as well. Do you, try to really regulate all these devices, or you say this is going to happen infrequently enough that I can count on ex post case by case enforcement action?
Frank, can you just help me make that distinction again that you were saying between the kinds of certification that you need to do or the kind of testing that you need to do? One is just for the, does it meet that requirement? The other was the potentiality to create interference.
Right.
And doesn't that depend on what you're creating interference to?
It does. So where noise is a phenomenon, interference is the effect of that phenomenon on a receiver. One receiver in a certain environment may not have any problem with the noise in the environment, another receiver might. So the regulatory limits that have been established, like for example, the 43 plus 10 log P limit that we saw in the earlier presentation, are meant to enhance electromagnetic compatibility between systems. But it is not, I think, ever possible to simply guarantee that an unwanted emission, a spurious emission, a noise type emission from some system, either an intentional or an unintentional radiator, absolutely will not cause interference in some kind of receiver. Again, has been remarked, we can put devices quite close to each other. If I have this phone too close to this receiver and it tries to do a little talking, now it won't do it for me. Everyone's heard the GSM gallop?
Yeah.
Exactly.
That's interference with the little speaker system. But things like that may need to be dealt with on more of a onesie-twosie basis.
Right.
I don't believe, and I'm only speaking personally here, not for the agents here, that it's not possible to simply come up with tighter and tighter limits until you say, okay, we've got limits that are so tight that we've now precluded the possibility of any interference from occurring.
Right. So that gets to the trade-off question that Julie raised as well. There's a question at the back there. Could we have the microphone, and would you please identify yourself?
Thank you. Jim Lansford. So you raised an interesting point. We have a Class B emission limit now for unintentional radiation, right? It's minus 41.3 dBm per megahertz. But that doesn't comprehend aggregation. And I know even Ofcom's talked about things like putting spectrum monitors around London just to see what's the real background noise and interference level is based on aggregation. Could you comment on is the minus 41.3 number the right number? Do we need something that's more dynamic, it changes with frequency, or is it more localized? So what would be your comment on the way we ought to manage these spurious unintentional emissions levels?
Well, there certainly are limits that do vary with frequency. For example, look up the emission limits for ultra-wideband devices, and you'll find that it's a somewhat complicated line drawing that goes across a spectrum that has peaks and dips in it, allowing different levels of emission from ultra-wideband devices depending upon what frequency band you're in. I would say that the limits that are in place are meant to reflect the existing state of the art that is achievable in devices that are manufactured, but always, as with any limit, trade-offs have to be made between the economics of what's achievable in manufactured devices versus the effects those devices could have on other systems due to their noise-like or unwanted or whatever emissions. And of course, regulatory structures are evolving all the time. So presumably, if needs evolve for different limits, then presumably eventually the regulatory structures will adjust to those needs. But there are multiple competing interests that are involved in coming up with limits on unwanted, out-of-band, spurious, noise-like emissions.
So I think, I understand that these are co-site limit, there's adjacent channel, and I believe the radios could just sense, and when they're co-channel, switch to another channel. But 20 years from now, it'll be so much cheaper to just switch channels and build filters and high-power transmit amplifiers that no one's going to worry about it, or very few people worry about it. It's much better to be frequency agile, move out of the way.
Assuming that there's somewhere to go.
Yeah, well, there's lots of spectrum out there.
Right. Another question? Yes, we have a question in the front, please.
Here, just a quick comment.
That way the folks who are on the live stream can hear you as well, Aaron.
Thanks.
You can just identify yourself.
Ira Barron, Baseline Telecom. While we're continuing with the metaphor that we like to talk about, comparing this to, let's say, water pollution, the good news is, as soon as we adapt, everything's clean. In contrast, we will never have to flush the PCBs out of the water supply. It's that.
So I didn't follow that. Can you,
Okay.
So explicate your metaphor.
Certainly, if we're drawing a pollution analogy to spectrum versus something like water, in water, the water is contaminated. So we have carbon dioxide in the oceans today. We have PCBs in the Hudson River. The cleanup of that is tremendously difficult. In spectrum, if we can't solve it with agile radios, we just we put in emissions requirements or interference requirements on out-of-band emissions, et cetera, on the devices, and everything gets cleaned up very quickly. So in essence, it's a much easier problem to fix than folks in other areas have.
Got it. Thank you very much. Let me just, I'll come back to the audience in a moment, but I just wanted to circle back on something, which is a number of you have said, look, we need more data. It would be useful to have data to inform regulation. We have at the table here the world experts on doing these measurements. Talk a little bit about, maybe we'll just take it from one end to the other, what it takes to do these measurements. Is it easy? Is it hard? Are there many people who can do this? Are there few people who can do this?
Well, I will say, I think one of the more challenging things in making man-made noise measurements is actually ensuring that your spectrum is free from the intentional radiators. That's a non-trivial thing, especially if you go out and you make a spectrum measurement one day, or even over a course of a few weeks. There's really no guarantee that if you're going to go and make a noise measurement after you've done your spectrum measurement survey, that spectrum is still free. It's a significant challenge, and especially if you were going to try to design a system that would automatically sense the spectrum and then try to make the noise measurement immediately after sensing the spectrum, that would add significantly to the complexity of the system.
I think that to do noise measurements well requires a substantial investment in the people and the hardware that will be used. The people need to have a thorough understanding of exactly what it is that they're setting out to do, and as you just said, Jeff, they need to have a thorough understanding of what the pitfalls may be, and they need to be able to solve those kinds of problems. And so basically I would say not simple, not cheap, definitely worth doing, but not a trivial undertaking.
Well, the challenge for us is we're doing these mobile measurements, and you don't know if you're coming up next to a 100-watt transmitter and adjacent channels. There's an awful lot of smarts of interpreting the data, and then the text. I've had techs go out and make measurements, and it all comes back corrupted. And his laptop was going low, so he plugged in an AC adapter, inverter into the car, and the whole thing was jammed. He had no idea. So it's real easy to mess them up. And you put them in the jam yourself, or have something else in the car with you.
Yes, there's
no.
There's no one easier to fool than yourself, and it's easy to take a lot of data thinking that the data were good, only to realize the data were not good.
Like you said, the antenna gets broken, so you have to have something you tune to know that it's actually measuring something.
You need to be able to know while you're taking the data whether the data are really good or not, and it's a reason why you need to have experienced, capable personnel doing it, I think, and not people who are basically just button pushers.
Unless you throw away half of it.
Or you're willing to take an enormous amount of material and kind of sort through the chaff to get to the wheat somewhere down inside.
Bob, did you have a comment?
Sure, I think there are all kinds of ways to do it easily and foolproof almost, but you do really have to design the measurement system very carefully to make the measurement system rules. And now I talked earlier about where we made our atmospheric radio noise measurements. There were guard bands around particular frequency bands. If we wanted to do this, we could just set aside 1% or a tenth of a percent of the frequencies as very particular guard bands where the only thing really allowed in there would be stuff that wasn't supposed to get in there. And then we could tune these receivers to that. And we'd have to have rules about, particularly if we were making measurements inside, which I think is a great place to make measurements, about how close you could get to particular kinds of objects and things like that, because you'd need to do that. And as I say, the system would have to be designed very carefully with the right set of rules, and it could be done. But all of this would be a fair amount of work.
So when I listen to what you're saying, this sounds to me like millions to tens of millions of dollars. No?
I think less.
Less? Give me a ballpark. So hundreds of thousands? Because one of the things that struck me looking at the little bit I've looked at the literature is that there are quite a few very good studies at specific locations.
Yeah.
But if you want to generalize to get many locations to get a comprehensive survey and actually make a statement that perhaps a regulator could put some store by or could defend in a rulemaking, you'd have to measure in lots of places.
Why
what
not
does
just,
that do to the cost?
If Verizon has problem A, B, and C, just help them diagnose. I would rather measure where they've had problems versus measure everywhere. If you focus on where people are having problems and understand the problems, it'd be much less expensive.
Right, right. Yeah, because that actually does change the balance. You know, I've heard somebody say that it's very hard to get government to fund any work. The only way you get money from government is if you can demonstrate that unless you do the work, somebody will die, and that you'll be blamed for it. You know, then you can get funding. And I don't think we're quite here, although something which Dale has spoken to is we're talking about a very important asset. I mean, the carriers have paid billions and billions of dollars for their licenses. They are suffering problems, and there might be value in addressing those. We'll have one last go around to see if there are any comments or questions from the audience. Nope. Very good. So my closing question, I just want to go down the table to see if anybody has any last thoughts. But the hardest question perhaps of this session is there anything that you think that regulators, whether they're in the FCC or in government, should be doing? Things that they don't understand sufficient, that they don't put enough weight on. Things that are undervalued. There's jump balls. Anybody want to start with that? Mark.
I don't think people clearly know what the problem is. Is it regulated devices that are aggregating up? Is it broken devices? I don't think they really know. No one knows what the real problem is. Yet we have these rules and this testing and all this cost. My laptop probably weighs 10% more because of the shielding, and it's unclear is it worth doing.
So I could hear that and say, well, you know, if Mark McHenry says we don't know if there's a problem, there probably isn't a problem.
No, we don't know what the problem is. Is it things that are broken and radiating by accident, or is it things, that's the biggest issue, I would think.
Okay, so your assessment is that there is an issue, but we don't have a diagnosis.
Well, after I find a problem, I don't pick it up and go do an FCC test to see does it meet spec.
Right.
I don't think people have ever done that.
Mm-hmm.
Track, like there's a lot of power line noises. Is that meet spec or not? No one's closed the loop. Measurements show this is bad. Is it illegal? What rule did they violate?
Right.
Until you get to that circle, you don't know what rule to fix.
Whose responsibility is it to do that work?
Julie.
Yeah. I would contend that it's the people who are suffering the losses, perhaps, that should
Well, it affects everybody. It's a broad problem. Why should company A pay for it to help everybody else?
Right, right. Collective action problem. Any other comments to close? Dale, please.
I would just more like to ask a question. You can do these very precise, limited measurements, really good scientific measurements, but on the other hand, we have millions and millions of cell phones out there who can make measurements and maybe even across different bands. So can you compensate for the fact that you don't have, you know, all the good scientific stuff, but can you, at least in part, overcome some of that with the fact that you can, in some sort of a crowdsourcing sense, collect millions of samples from millions of people hourly, practically.
And that's a very good place to close. We actually have a few minutes. We'll get the next panel set up. But the next panel will pick up in a way in what Dale has just said, because it's the panel of people who are actually out there in the field running services. And we want to learn a little bit about what the carriers are seeing, what are the problems that they're having. They're the guys who actually have the devices, and perhaps that's one way we can get the data. So please join me in thanking this panel.